from Montgomery County Public Schools, and he is speaking on the trapezoid debate as a vehicle for discussing definitions in mathematics.
All right, well, thank you, and thank you for organizing. I'm John Chase. I'm a high school math teacher from Maryland, and I'm going to talk to you today about trapezoids. And I promised some general comments about definitions, too, as they come up here. In a minute, I'm going to poll. I want you to think about it for a second, but I'll do some audience participation here. I'm going to ask you to weigh in on this. There's multiple, maybe you didn't even notice if you're walking in. There are like multiple definitions for the trapezoid. You're going to vote in a minute whether you prefer the exclusive definition, that is, a trapezoid is a quadrilateral that has exactly one pair of parallel sides. Or you could vote for number two. I prefer the inclusive definition, which is that a trapezoid has at least one pair, a quadrilateral that has at least one pair of parallel sides. Or I'll give you the out as well. You can say it's a tie. So a lot, actually, some of you might be surprised that this is like a heated debate. But it is in certain quarters. Over the last 10 years or so, lots of people have been talking about this, at least in some of the circles I travel in the online math education community. And people are excited about this. You could spend a lot of time talking about it. And people have, and people might even give an hour-long talk on it. And I did that with a friend and colleague at the National NCTM annual conference a few years ago. But I'm going to try and boil it down to a 15-minute thing here today. And we, in this debate that we staged, looked like that. We kind of did a natural incrementing from weak arguments to strong arguments. Because of the format today, I'm going to just hit you right away with all the strongest arguments on both sides of this issue. Okay. Lots of buzz. We also made buttons, right? Like good political campaigners. I took one side and he took the other. Okay. So are you ready to vote? I've given you a second to think about it. So how many people are voting for one? You're an exclusivist. Okay. I'm gonna say that's half. Okay. What about two? Oh, interesting. What a great split. And then there are some people who are fence riders. Who are you? Okay. Good. That's like philosophically neutral. I appreciate that. So let's get into it. The status quo, the state of affairs is, of course, that in traditionally, the trapezoid was defined this way, as a quadrilateral with exactly one pair of parallel sides. And so actually, the diagram is, if you're being very precise as a geometry student, then the diagram's not quite right. I guess if that's true, then we should really have those, right? We should insist non-parallelism for the legs, right? Okay, so that's the exclusive trapezoid. And by the way, every time I'm going to show a slide that kind of defends the exclusive trapezoid position, it's going to be on a maroon slide like this, just to help you keep score. This definition gives rise to this kind of traditional hierarchy under the exclusive definition, where trapezoids enjoy kind of their own spot off to the side. They're their own thing. And honestly, this has worked for a lot. This is like the status quo, and this is not like a terrible argument. The argument from tradition, it works. If you see a fence somewhere randomly in a field, before you tear it down, you might ask why it's there, right? So that's the idea here too. Is this does seem to work. It's been in the textbooks. We've done lots of proofs using it. It works. So why change? I think the burden of proof that is on the inclusivists is the point. Okay, so blue slides for the inclusive trapezoid. So what's the definition of the inclusive trapezoid? It's the definition I already said. But what does that entail? Some of you have already thought about it, what it entails. It means that as we do this, there's a moment at which the trapezoid maybe becomes a parallelogram. Yeah. And so the inclusive trapezoid person would be like, yes, that's exactly what I want. I want that to be the case, that the parallelogram is like a child of the trapezoid. And the inclusivist, really, I think this is the strongest argument for the inclusivist, because you have these kinds of inclusions among all the other quadrilaterals. This is the inclusive hierarchy that definition gives rise to, where not just a parallelogram, but also a rhombus and a rectangle and a square are instances of a trapezoid as well. So you might think, well, that's kind of elegant. There's no argument about a square being a rectangle. right? In fact, imagine a world where suddenly we declared that rectangles were something, that squares were not rectangles. We would like immediately change things back, right? We'd be like, that doesn't work, because there are all these results about rectangles that we'd like to apply to squares. And so we'd be like, that's not desirable. And you think, well, the same must be true about trapezoids and parallelograms. Maybe there's like, and that is true. In fact, for example, the area of a trapezoid has, as a special case, the area of a parallelogram, for example. Like, slam dunk, checkmate, right? So this is clearly the best definition of the trapezoid. There is another good argument for inclusivism, and that's that mathematicians in general, when they make definitions, we often like to leave things kind of open. So here's a quiz. Which of these is a trapezoid? Now, if you've been listening, then your immediate follow-up question should be, under which definition, right? So if you're, let's start with if you're an inclusivist. Yeah, they're all, right? That one, and also that, and that one, and that one, and that one, and that one, and that one. They're all trapezoids, right? We just went through that. What if you're an exclusivist? What's the answer? Yeah, A and C, I hear you say maybe. Or wait, and then you look at C and you're like, well, I'm not sure. Actually, if you're an exclusivist, I think you have to bite the bullet and say you're not sure about any of them. Because remember, I told you, geometry teachers are very big sticklers about this, right? Are you sure that, and even an A, that those are non-parallel? How can you be sure that's an exclusive trapezoid? And that seems like a little bit cumbersome to always have to specify that. So again, slam dunk for the inclusivist, right? Also, we like that. As the inclusivist, I might say, this is what we do with mathematical structure. When we make statements about groups, we want to be able to say about a ring everything that's true about groups as well, right? This is like just the hallmark of mathematical thinking. So you'd be like, okay, well, we're done. Inclusivists win. Oh wait, let's circle back, because there's actually a fairly significant snag that I think, even though it's pretty easy to think about, that most people don't think about in this debate. What is an isosceles trapezoid? An isosceles trapezoid, in the most basic sense, is, even from the linguistic origins, is a trapezoid that has equal legs. That's like literally what it means. You see the problem for the inclusivist, though? It means that for the inclusivist, that what else is an isosceles trapezoid? A parallelogram is an isosceles trapezoid, and I think that's probably even for the inclusivist. I think that for most inclusivists, that's probably a bridge too far. For example, you might want to be able to say that for an isosceles trapezoid, that the base angles are equal. You can't anymore if you're an inclusivist, right? So I think that's a little bit of a problem. Let me just show you an example of how a proof goes if you're an exclusivist. Here's an example of one proof that you might see in a geometry textbook. Let's prove that if the base angles are congruent, then that's sufficient to show that the trapezoid is isosceles. The way a proof might go is like this. Since the legs are not parallel, extend them until they intersect. Since the base angles are equal, the small triangle and the large triangle are both isosceles, and then by segment subtraction, you get the desired result, right? Now, notice there's one key phrase that you all should be highlighting in your mind. What is that? Yes, since the legs are not parallel. Notice that the exclusive definition is not kind of in the periphery, in the background, like a decoration here. The exclusive definition is actually critical. Like this proof doesn't technically isn't worded right. If you're using the inclusive definition, you can't be sure in the inclusive definition that you can say that. Okay, see how you're coming around? Now you're going back and forth, I can see in your mind. So how do you do it if you want, as an inclusivist, still to have this notion of, well, we kind of all know what we mean, though? Well, there are a couple different solutions that people have. I like this one. Symmetry is an interesting way to actually, there could be a case made that symmetry could be the way we define all the quadrilaterals, actually. And that's kind of a fun thing to go. We're not going to go there right now, but that's kind of a nice way to do it, because in a sense, that's maybe what you always meant by an isosceles trapezoid. I'd be like, I want it to have this property, this symmetry. It's beautiful, that's what we want. So let's see if that works. I'm going to prove the same result, blue slide, but under the inclusive definition, okay? The same result. Might sound a little weird, but here's how we'll do it. Construct the perpendicular bisector of the bottom base. Since the bases are parallel, that is also going to be perpendicular to the top base. And then we have like kind of two quadrilaterals, one on the left and one on the right, and they're congruent by ASASA. Most geometry students aren't used to using that property, but it's a thing, okay? And then therefore we get the segments on the top are equal, and therefore the yellow line is the perpendicular bisector of not just the bottom, but also the top, which shows the midline symmetry we want. I don't know, so maybe you like that. By the way, because of the short format of this talk, one thing that I think is important for you to maybe see is if you go, I have the QR code, if you didn't catch it at the beginning, but at the end you can go and check out the slides. In my appendix to the slides, I have a whole bunch of, like, kind of all the traditional trapezoid proofs done with the exclusive and with the inclusive definitions. This is just one example side by side, okay? I do want to highlight one other proof. Okay, so imagine you want to prove that for an isosceles trapezoid, the diagonals are congruent. Here's how that might go. You might consider, you see in the back of blue highlighted triangle, and then you also might consider the blue highlighted triangle there, and then by SAS reason that they're congruent, and then the fact that the diagonals are congruent follows. But notice if you're an exclusive trapezoid person, then you also have to, if you're an exclusive trapezoid person, you would also have to do this proof. Why? Well, because a rectangle isn't a trapezoid, right? But notice that the proof over here is basically the same, isn't it? I mean, it's really the same arguments. Highlight a triangle, and then show that they're congruent. So I think this is a strong case, again, for blue slide, for the inclusive team, right? It's like we don't have to do both of those proofs. All right, so that's the inclusive, I think, some of the strongest arguments for the inclusive side. So one more thing, though, to say about the exclusive position, which I think is a very strong thing that we kind of maybe forget when we reorder the hierarchy of quadrilaterals. Just to remind you what a metric versus an incidence relationship is. A metric relationship has to do with size, measurement, shape, right? So the length of this segment is longer than the length of that segment. That's a metric relationship. An incidence relationship, though, is that these two lines meet at point L or point M or whatever. These two lines intersect, etc. So notice that there's actually kind of an incidence discussion to have here. There's a way in which trapezoids and parallelograms differ in a way that's maybe perhaps even more fundamental than metric relationships. Because if you extend, as we've already seen, if we extend the sides of the legs of a trapezoid, they meet. But for a parallelogram, they don't. And that is maybe in some ways like a more fundamental relationship than even, that precedes even metric relationships, right? Like the idea of things even meeting is something that's even more basic. And so you can now think, oh, maybe that's why in the very first place the hierarchy was structured in that way, right? Because it was ordered by incidence relationship, and then following that by metric relationships. So how do we come together on this? Well, first let's summarize. I'm going to give you 30 seconds to just review the both sides here. Take a second, look. And then I promised some comments about the kind of the implications for other definitions in math and math education in general. So let me say that just briefly, 2 slides on that. First of all, implications for math in general. Well, first of all, with trapezoids, what would be one solution? Well, one solution would be like just have 2 names, right? Like we could just start calling them exclusive and inclusive trapezoids, or trapezoids and truncated triangles, or like we could come around this. If both are really useful, then like maybe that's worth doing, But this is obviously not just about trapezoids. By the way, it's worth mentioning that every definition is exclusive and inclusive, right? Like that's what it means to be a definition. It separates set A from things that are not in set A, right? Every definition like kind of draws a line between things and other stuff that isn't those things, right? Follow through on consequences to determine elegance and power. Like I said, in these conversations, there was a lot of heat, a lot of smoke, and not a lot of fire. A lot of people hadn't done the work. And so that's why we said, me and my co-debater, we said, we got to prove all these things. And like I said, these are in those slides if you'd like to look, to see whether they are clunky or whether they're elegant. You don't know, really, until you really wade in and try it. And then for math education, here are my takeaways there. Teach the controversy, let this kind of come into the class. There's no reason that you can't let students talk about this too, be part of the conversation. I think it's important to say that this is a human part of mathematics. Nobody owns math. Everyone can participate in this, even from not just college level mathematics, but also all the way down to elementary school students can weigh in on trapezoids, can't they? It's important, I think, to realize that for people to realize that math isn't finished. And then lastly, be gentle with others. There are like compelling arguments on both sides, and there are people that were really going at each other. So, like, maybe just calm down in these kinds of debates. Don't make it personal. It's actually quite fun. So I appreciate your time, and let's invite some discussion. Yeah, thank you. Okay, yeah, I knew this would be exciting. Okay, go ahead.
So I was really interested in what you said about the incidence versus method. And do you know, so because I think like geometry is over finite fields, like affine planes over finite fields, when you don't have methods, but you talk about parallelisms, distances. Have people explored this question in that finite coordinate sense?
I would say no, but first of all, to that question, I did want to say one more thing about that though. I mentioned on the summary slide, you might have caught it, but I didn't say it in the talk. There's actually kind of a linear algebra argument here too, because if you think about it, take a square and perform a linear transformation on it. What can happen to it? And the answer is it can become, well, it can become a parallelogram, it can become a rectangle, it can become a rhombus, right? But what can't it become? A trapezoid, right? Under any linear transformation, right? So there's something that kind of belies the fact that there's maybe something there. There's like something inherently different for the exclusivist.
Perhaps platonic.
Yes, maybe even platonic, yes. I saw another hand somewhere over here. Go ahead, please.
Well, you compare it with, let's say, the argument about whether one is a prime, and the fact that that was an active discussion for quite a while. Hardy in his first edition of Pure Mathematics says one is a prime, and then finally the mathematical community on the whole has come down on the, I mean, what you could say is, look, I mean, right now at least it's an active discussion. Is there any guarantee that we won't come down on one side or the other?
Yeah, can you pull up that quote again, Christopher?
Yes.
Did anyone go to the quotable math session with Ben Orlin yesterday? One of the quotes I took a picture of is this one. I sent it to Christopher. So my
oh man, my timing is so bad.
No, it's okay, it's okay. I might be able to remember. He said something like, this is Vladimir Arnold. It's impossible to understand an unmotivated definition. And I thought, I've got to share that with my people tomorrow. Because isn't that true? Like, you kind of, a lot of times, and there were some other good quotes about that too, that like a lot of times don't we kind of start with the thing we want to be true, and then work backwards to the axioms and the definitions that would support that, right? And that's kind of the case with the prime situation, right? We're like, well, the fundamental theorem of algebra, of arithmetic doesn't work otherwise, right? You know, this unique factorization doesn't hold, yeah. Thanks.
This is sort of a question for the whole room. I'm just interested to see if anyone changed his or her mind.
Oh, thank you. Yes, yeah. Anyone? At least, Let's ask. Anyone change their mind? Okay, you flipped. Even though you gave very what I think is kind of. By the way, can you tell which I was in the debate? I was an inclusivist at the time. I think I've kind of come around. I really do see the light, and I think both sides are equally compelling at this point.
Red and blue, and I'm like, red is more like,
Oh man, okay, you're psychologizing here. Yeah, it might be true. Anyone else have a change of mind? Go ahead.
So when you are introducing this activity to your students, do you preamble this that there are other geometries out there?
Yeah, it doesn't really come up in high school math, obviously, very much. But obviously, any chance you have to hint at non-Euclidean geometry is a chance you want to take, obviously. Say it again?
Hyperbolic geometry.
Yeah. The thing I would say about that is that
your students at least would be exposed to the fact that there are other geometries. This is not just the only way to think.
It is worth mentioning that another reason to be gentle in this debate is that trapezoids actually don't get a lot of press. Like, they just got a lot of press right now. But in the curriculum, they don't get a lot of press. Like, you might do a day on trapezoids, right? Like some no days. It's either 0 or 1 though, usually in a high school geometry setting. So it's like, maybe it's not worth getting too fired up about. In the back.
I think in regards to that, from other geometries, a better example of definition there is actually the definition of parallel. Because Lobachevsky, when he developed hyperbolic, he did it by changing his definition of parallel, not by the way that we did teach it. There's 2 lines. Rather, he changed his definition of parallel.
Yeah, yeah. Thank you for that comment. How are we doing on time? Do we need to wrap? We take one more, two more? Oh, great. I have some other things I can mention too that I wouldn't mind sharing if you like, but let's hear another question. One thing I thought I'd mention too is some of the non-arguments that are out there a little bit. And I have some slides in the deck about this if you'd like some of the non-arguments, but I didn't want to lead with those. I was like, let's just get out the strong stuff. One is that draggable trapezoid is quite compelling. But the thing you don't know about that is that that's kind of question begging, actually. It's very easy in dynamic geometry software to also construct a trapezoid that's an exclusive trapezoid that as you drag it around, it can't become a parallelogram. How, you ask? Well, here's the way you construct it. You start with a triangle, and then you build a segment parallel to one of the sides, and then you hide the triangle, and then you start dragging it around. Guess what it will never be? A parallelogram. And so the draggable argument is not actually a slam dunk. It's actually kind of it is actually kind of question begging, actually. You can easily construct a dynamic exclusive trapezoid too. And there's some other good kind of non-arguments. There's a lot of people talking about the trapezoid rule in calculus also, and that kind of bears nothing. That wins no points really on either side. On either side, it's like, okay, whatever.
Yeah, I'm sort of, so I'm the exclusive category. Part of my reason, I guess, is that it comes from triangles in a way.
Yeah, it's like a truncated triangle.
Truncated
Yeah.
triangle, and nothing else does.
Yeah. Yeah, I think that's a very persuasive argument. Go ahead, Mike.
Yeah, there's also thinking that going to kind of an affine versus projective, as you move from affine to projective, all your parallelisms go away. So one could conceive of the parallelogram as being a projective trapezoid, right? Like once you put that trapezoid in the projective plane, yeah, you lose all your parallelisms, so it becomes a trapezoid. So I don't know if you ever engage your high school students on projective geometry. Not high school, I do a little bit of that, but I never thought about that.
Yeah. Good comments. Anyone else with either comment or question? Thank you guys so much.